Today we're going to talk about electrocyclic ring closures and whether or not they are allowed or forbidden. There are typically two pathways whereby electrocyclic ring closures or openings can occur. Chiefly these are influenced by the type of energy that you apply to trigger the reaction, so thermal energy versus photochemical energy or photons, while the other factor is the number of electrons that participate in the pericyclic transition state. Each combination of these conditions will typically result in either an allowed or a forbidden pathway, and these pathways often determine the stereochemistry of the products that you see. So because of this, it's important to know which pathways are allowed and which are forbidden. And there's two methods that have been put forward to do this: frontier molecular orbital theory as well as the Dewar-Zimmerman model. So we're going to cover both of these before we start getting into specific examples. So to start with, we're going to look at frontier molecular orbital theory. We'll focus on a simple example, the butadiene shown up here in the corner. And if we consider the p orbitals that make up this butadiene, we can see that there are 4 electrons that inhabit these p orbitals. Now in the ground HOMO state, we can see that this arrangement of p orbitals is in effect, giving us one double bond adjacent to a second double bond here. From our knowledge of pericyclic ring closures, we can take this molecule and cyclize it to give one of these two products shown down here, each having differing stereochemistry. Now, in order to get two unique stereoisomeric products, there needs to be two unique ways that the orbitals can come together, combining to give the new bond which is shown in pink. One way is a disrotatory closure, whereby these outermost p orbitals combine, one in a clockwise fashion, one in a counterclockwise fashion, shown in red and blue. The other way this could occur is in a conrotatory fashion, whereby both orbitals rotate in the same direction. So in this example, it's shown as both rotating in a clockwise fashion, bringing the orbitals together in that way. The way whereby we control this process comes down to the source of energy that we use to facilitate the reaction. In 4-electron systems, to get the disrotatory closure, we use photochemistry, so a photon, to deliver the energy which causes these orbitals to rotate together and bond. Taking another look over here, if this is the HOMO state, when the molecule absorbs a photon of energy, the HOMO gets promoted to the LUMO state, the lowest unoccupied molecular orbital. If we look at the arrangement of these orbitals, we can see that there's going to be a double bond in the center and two non-bonding orbitals with the same phase either side of it. And this is the situation that we've shown over here, with our bonding orbitals at the back and two p orbitals with the same phase on either side. Now, in order for a bond to form, we need the phases of these outer two p orbitals to combine together, whereby the same phase matches up. And that can only occur with disrotatory closure. So this phase bends in this direction, this phase bends in this direction, until ultimately we get this alignment of the two phases of the outermost p orbitals, and that gives us our brand new bond shown in pink. Now, this isn't what occurs for the thermal route. Here we keep the same arrangement of the p orbitals here, and that means that these outer two most p orbitals have mismatched phases. When you give this molecule the energy that it requires to bend these outermost p orbitals towards one another, the only way that the new bond can form is if both orbitals rotate in the same manner, giving conrotatory closure. So this phase bends in this direction, this phase bends in this direction, both phases line up together, giving you the new bond in pink. And the main outcome of this is that the stereochemistry is going to be different in the two products, based on the difference in rotation that we see in the outermost p orbitals. So if those are the two ways that this pericyclic reaction can occur, there are equally two ways that the pericyclic reaction cannot occur. So by the photochemical route, conrotatory closure is forbidden. If both of these outermost p orbitals rotate in the same direction, we're going to get mismatched alignment of phases of those orbitals. If two orbitals with different phases overlap, there is no bonding interaction seen at the end. So effectively, there's no stabilization. You're not going to get a cyclic product in that manner. Same thing occurs by the thermal route if you try to apply disrotatory closure. If you rotate the outermost orbitals in differing directions, same thing occurs. You're going to get overlap of two orbitals with different phases, and that's not going to give you a bonding interaction. So you can't get a cyclic product in that way. But beware, the second factor that influences these reactions is the number of electrons in the pericyclic transition state. So where previously we were talking about 4 electron systems, if we now look at 6 electron systems, like a hexatriene, all the trends we just talked about are going to flip around. And the fastest way to see why is to just compare the HOMO and LUMO states. So if we take a look at the previous example, we can see that the HOMO state, our outermost p orbitals have mismatched phases, and then when we get up to the LUMO state, we have matching phases on the outermost orbitals. But for a 6 electron system, the HOMO state has matching phases on the outermost orbitals, while the LUMO has mismatched phases in the outermost orbitals. So the situation flips around. For this reason, when you apply photochemical activation, what you need is conrotatory closure. So here we've recreated the arrangement of p orbitals to match the LUMO state over here. The outermost p orbitals have mismatched phases like we see over here, so the only way we can bring matching phases together to create our bond is by conrotatory closure. The opposite is true under thermal conditions, where in these outermost p orbitals, the only way to line up the matching phases is for disrotatory closure to occur, which matches them up like this, giving us our new bond shown here. This means that the stereochemistry you're going to see is going to be very much influenced by the number of electrons in the pericyclic transition state, as well as the types of energy you are using to trigger bond formation. And much like before, if we talk about the allowed pathways to give us these products, the opposite pathway is going to be forbidden. So in a 6 electron system, if you have thermal activation of the bond, conrotatory closure is going to be forbidden. Similarly, if you use photochemical activation, disrotatory closure is also going to be forbidden. We can summarize those trends. For a 4 electron system, you're going to see conrotatory closure under thermal conditions, whereas in a 6 electron system, you're going to see disrotatory closure under thermal conditions. Now, up until now, we've been focusing on ring closure reactions. So talking about these 2 examples, if red is a clockwise rotation and blue is a counterclockwise rotation, we can see the routes whereby the outermost p orbitals twist in order for the bond to occur. But we can also think about this in terms of the back reaction or the ring opening reaction. So if going from here over to here was clockwise rotation, to get back you then need counterclockwise rotation. And the same is true for disrotation pathways. So if here was counterclockwise and this was clockwise to get us over to here, to get back we need clockwise and counterclockwise, the reverse of the pathway to get there. And it's worth noting that if a ring closure reaction is allowed, the same opening pathway is also going to be allowed. Or said another way, if the forward reaction is allowed, the backward reaction is also going to be allowed. This slide simply gives a summary of the way that 4 electron systems, as well as 6 electron systems, behave under both thermal and photochemical conditions. So in the beginning I said there were 2 different models for determining which pathways are allowed versus forbidden. That basically concludes frontier molecular orbital theory. What you need is quite a good understanding of the HOMO and the LUMO states of whatever system you are looking at in order to be able to draw out the orbitals and then visualize twisting them and figuring out where overlap of phase is going to occur. If you see destructive interference, so p orbitals with different phases overlapping, that is not going to give you a bonding interaction, therefore that's a forbidden pathway. Now we're going to look at the alternative model for figuring out whether these pericyclic reactions are forbidden or allowed, and that is the Dewar-Zimmerman model. This model still looks at molecular orbitals. However, we don't need to remember the HOMO and the LUMO arrangements of the systems that we are looking at. All we need to know is the number of atoms participating in the transition state, and then we assign them p orbitals with arbitrary phases. So here, the easiest one to assign is just have all the orbitals have the same phase. Like before, we have the understanding that the outermost p orbitals need to rotate and come together in order for a bond to form. And the first step is we simply link together the same phases of the orbitals like so. After we've done that, we're going to rotate the outermost p orbitals in either a conrotatory or a disrotatory fashion, and then we're going to draw in the new bonding interaction that occurs, which I have highlighted here in green. After we've done that, we ask a question, which is how many mismatched phase bonds have occurred by whatever rotation method we've chosen, be it conrotatory or disrotatory. Looking over here on the left, keeping our initial pink bonds intact and drawing in our new bond in green, what we can see is that all the bonds that we've drawn have the same phase. So there are no mismatched bonds occurring by this method. Given there are 0 bonds with mismatched phases, we're going to class 0 as an even number. Therefore, this is going to be the Huckel topology in our product. Looking on the other side, when we rotate the outermost p orbitals in a conrotatory fashion, we keep our initial bonds in pink, then we draw out our newest bonding interaction, and we can see that now we have one bond that has mismatched phases. So because there is one is an odd number, therefore this product has a Mobius topology. Now, if FMO theory requires you to remember the HOMO and the LUMO arrangement of orbitals, this Dewar-Zimmerman model requires you to understand whether or not the products are going to be aromatic or anti-aromatic. And the rules for this change depending on whether your transition state has 4 electrons or 4 electrons plus 2, i.e. 6 electrons. That's going to account for the different results that we're going to see for butadienes and hexatrienes. So we determined before that this has the Huckel topology. We have 4 electrons in our transition state. That means that this transition state is anti-aromatic. Looking over here, for this one, we determined that this transition state has a Mobius topology. It still has 4 electrons, therefore it's an aromatic system. So using the Dewar-Zimmerman model and looking at the orbital phase inversions rather than a holistic view of the molecular orbitals, you really need to sort of memorize or look up this table, allowing you to apply whether or not it's a Huckel or a Mobius system, and then look up which one of these is either aromatic or anti-aromatic, depending on whether you've got 6 or 4 electrons in your transition state. The rule that's constant is that if your transition state is aromatic, the reaction is going to be thermally allowed, whereas if your transition state is anti-aromatic, the reaction is going to be photochemically allowed. But ultimately, the information that you get between these two methods of working out whether your pathway is allowed or forbidden, it gives you the same information at the end. So you only need to really understand one well because they're redundant approaches. So to summarize, both frontier molecular orbital theory and the Dewar-Zimmerman model provide you with useful information regarding which pathways are allowed or forbidden. Whichever method you're going to choose, the number of electrons in the transition state, as well as the source of the energy to facilitate the reaction, be it thermal or photons, is going to influence what answer you get. Now, both FMO theory and the Dewar-Zimmerman model, they give you analogous information. So once you have an answer from either of those theories, there's no need to attempt to the other one. The main difference is the two methods require different precursor knowledge. You either need to know about bonding and anti-bonding orbitals per frontier molecular orbital theory, or you need to know about aromatic versus anti-aromatic systems for the Dewar-Zimmerman model. So that's it for this episode. Thanks for watching.